Hey everyone, it's Suraj, and today we're going to be walking through discussion 8 from the spring 2019 iteration of Data 100. So this discussion we didn't actually walk through in person because it was canceled because it was right before spring break, but it contains a lot of important information that you definitely need to know for your upcoming midterm. That is, if you're watching this in spring 2019. So how this will work, we'll go through the notebook, but whenever I think we need to do some math, we'll switch to the iPad. Okay, let's get into it. So this discussion is on loss minimization, so modeling, estimation, and gradient descent. So why don't we start running it? Great. Do all of our grade imports. And so first, let's take a look at what our data set looks like. Okay. And so the first consideration we need to make is choosing what our model will be, how we're going to predict the y values given our x values and some weights. Okay, and so in this one, we choose f of x is equal to theta times x, which is really, since x is just a single scalar, is really just a line of the form y is equal to mx. Okay, so there's not even an intercept term, it's just a line that passes through the origin. Okay, so what we're going to do when we try to minimize the loss is try and find the optimal theta that minimizes some sort of loss function. And as we're about to see, we're going to be using L2 losses. Okay, so let's take a look. So first we need to define our linear model in our code, which is just taking an x and theta and multiplying them, so that's good. And now we're told that we're using average squared loss, which is average L2 loss, which we get by taking y actual minus y predicted, which is what we have here, y minus y hat, squaring that and taking the mean of that over all of our n data points. So we define that, and now we can visualize what this loss function looks like, and you can see that the optimal theta for our data set should be around 1.5. Okay, and that's something we're going to confirm after we get an analytical solution and plug in our values. Okay, so the first question we really need to look at is determining an analytical solution for the optimal theta hat for average squared loss. Okay, so we can switch to the iPad. And so we're told that our y hat for any one point is just theta times xi. You can see y hat I is theta times xi. Okay, so the loss for a single point, so I can say the loss for point I is just yi minus y hat I squared. This is just for a single point, okay? But since we know y hat I is just theta xi, so we can say this is yi minus theta xi quantity squared. And now our empirical risk is just the average loss over all of our n data points that we're given, right? So our risk, which we formatted as risk in terms of x, y, and theta, is the sum over all of our data points of yi minus theta xi, quantity squared, and it's really the average of that. So we multiply by 1 over n out front. And now what we want to do is find the optimal theta, so the theta that minimizes this empirical risk. Okay, and how do we find minimizers? Well, we take the derivative, or partial derivative in this case with respect to theta, set it equal to 0, and solve. Okay, so let's do exactly that. So the partial derivative of our risk, excuse me, with respect to theta is, it's still going to be 1 over n times this sum. Now we just need to find what the derivative of this thing is with respect to theta. Well, the derivative of box squared with respect to theta will just be 2 box times the derivative of box with respect to theta. Okay, just by using the chain rule. Okay, where box is just yi minus theta times xi. So I can write this as 2 times yi minus theta xi. Now the derivative of whatever is inside the box with respect to theta, the yi is independent of theta, and so then it just becomes negative xi. Okay, and this is what we're going to end up setting, equal to 0. And so before that, let's do a little bit of simplification. So we can write this as 1 over n times the sum still. And what I can do, and I can pull out the 2 out in front actually, because it's just a constant. And I can write this as negative xiyi plus theta xi squared, because the 2 negatives cancel out. And of course, we're going to set this equal to 0. And what we can actually do is separate this into 2 separate sums, okay? And I can also multiply both sides by n over 2 to get rid of the constant because it's set it equal to 0. So what I'm really saying is I can write this as the sum from I is equal 1 to n of negative xi yi plus the sum, where I goes from 1 to n, of theta xi squared is equal to 0. But theta, again, is just a constant, right? It's independent of these i's. So I can pull it out front and say that this is the sum of the squares of our x's times theta, and that's equal to 0. But again, I want to solve for theta on its own, and so what I can do is move this term to the other side by adding by it, right? And so I can add the sum of xi, yi to both sides, and I get theta times the sum of xi's squared is equal to the sum from I is equal 1 to n of xi times yi. And now I can just divide both sides by this term to solve for our optimal theta. So that gives us that our theta optimal, or we can just say theta hat, is equal to the sum of our of the dot product you can think of as our x vector and our y vector over the sum of the squares of our x values. So in this specific case, when we're using the L2 loss function, or average L2 loss, and our model is theta times xi, this right here is the solution for the optimal theta. Okay, so now that we have that, we can implement it in code and see if what we have is correct. Okay, so write our answer here. We sort of already did that. So now that we have the analytical solution for theta hat, implement the function find theta. Okay, so what's theta hat? Well, it's the sum of x times y, and we can do that because everything's vectorized when we're using NumPy arrays, over the sum of x squared. That should be okay. And it tells us theta hat is 1.5502-ish. And as we saw up here, approximately theta hat is 1.5. Okay, so let's run the test to see if we're correct. Okay, our answer is correct because if you see what we have here, it's very close to what they have, whatever. It's correct. I'm not going to lie to you. Okay, so now let's plot our risk function along with visualize, but we will draw a line at our optimal theta hat that we found using this solution that we just solved for. Okay, and you can see that the expression that we came up with is correct because it finds the smallest value of our loss function, right? So that when you plug in the optimal theta that we found, it minimizes this loss function, which means everything we did was correct. Okay, and now what we can do is plot our y hat, so our model, or our model in terms of the theta that we found versus the true data points. Okay, and so you can see it does an okay job, but it's not really capturing the true essence of the model because it seems like there's some sort of sinusoidal business going on with our actual data points, but with our line just y is equal to theta times x, it isn't really able to capture that well. Okay, but for now, we're doing okay. And so what we want to do is visualize the residuals, which is essentially just how wrong each of our predictions was. So y minus theta hat times x. Okay, and so you can see the residuals, of course, they're centered around 0. So we have as many predictions that were too big as were too little, which is, of course, to be expected. But you can see they vary pretty greatly. Okay, so we want to do a little better. Okay, so now in question 2, we're changing our model from being just f of x is equal to theta x to being f of x is theta 1x plus sine theta 2x. Okay, so instead of just having a single theta, theta is really just a vector comprised now of theta 1 and theta 2. But the thing is, one thing you should note is this model is actually not linear because we're taking a sine of theta 2. If we wanted this model to be similar but actually linear, it might look something like theta 1x plus theta 2 sine x, but that's not what it looks like. So it's not linear in this case. But that's an aside. So what we want to do in this question is using the average squared loss, compute the partial derivative of our risk with respect to theta 1 and with respect to theta 2. And in 2b, we're just going to implement that in code. And then we're doing all of this so that we can run gradient descent to find the optimal theta in this model. Okay, so this one, all we're doing analytically is just finding the partial derivatives with respect to theta 1 and theta 2, and then we will let gradient descent do the rest of the work of finding the optimal theta. Right? This is in contrast to what we did in question 1, where we actually manually found an expression for the optimal theta. So we're not going to do that here. So again, our model is f of x is theta 1x plus sine theta 2x. And so our loss for a single point, we'll say, is again yi actual minus yi predicted squared, which in this case is just yi, minus theta 1 xi minus sine of theta 2 xi, all squared. And so then our risk, in terms of all of our x's, all of our y's, theta 1 and theta 2, is the average loss over all of our points. It's the average of this thing. yi minus theta 1 xi minus sine of theta 2 xi squared. And so what we want to do is find the partial derivative of this risk with respect to theta 1 and with respect to theta 2. And all we really need to do with this is implement it in code, right? We need to fill in these functions dt1, dt2, and dt. So we don't need to simplify it that much. We just need to get it to a stage where we can implement it in code. Okay, so that's what we'll do. So first we'll find the partial derivative with respect to theta 1. Okay, so as we've seen before, this will still be a sum over n points. And again, the derivative of box squared with respect to something else is 2 times box times the derivative of box with respect to theta 1. So again, to state that again, so the derivative of box squared with respect to theta 1 will be 2 times box times the derivative of box with respect to theta 1. Again, using our chain rule. So we can have 2 times yi minus theta 1 xi minus sine of theta 2 xi. Okay, let's clear up some room. Now times the derivative of whatever is in this box with respect to theta 1. So we notice that the first term and third term both are really independent of theta 1. So all this ends up being is the derivative of this thing with respect to theta 1, which is just negative xi. And really that's all we need to do for this problem. Okay, because again, we're just going to implement this in code. For theta 2, we'll follow a similar procedure. Again, it will be the sum over n points, 2 times the same thing, but now we multiply by the partial derivative of this thing with respect to theta 2, and now the first 2 terms are independent of theta 2, so they drop out, and we're left with the derivative of this thing with respect to theta 2. So what it will end up being is negative xi cos theta 2 xi. Okay, and that's just using the fact that the derivative of sine theta is equal to cos theta, and then when we multiply by a constant inside, we end up bringing that outside due to the chain rule. Okay, so I believe this is all we really need for 2a. So now let's hop over to 2b and implement this in code. Okay, so cool, that's good. And so now what we need to do is, and we're told that np.mean does the same thing as np.sum divided by the length of an array. So we can say our value will be np.mean of, and now we're looking at the first one, so 2 times y minus sine model, I believe is what we called it, yeah, of x theta 1 and theta 2, and actually we should say theta 1 is equal to theta at 0, oops, and theta 2 is equal to theta of 1, right? Because we're passing a vector that looks like theta 1 comma theta 2, so I just get the first one to be theta 1, second one to be theta 2, so I pass it into the sine model, which is what we have over here, and then I multiply by negative x, okay? So then multiply this whole thing by negative x, or I can even just multiply it by x and put a negative out here. Doesn't really change anything. So I can just return RV. Great. So that's just an implementation of what we analytically found the derivative with respect to theta 1 to be. We'll do almost the exact same thing for theta 2. So we'll take the mean of, and again, I can just write this as negative 2 times y minus sine model of x theta 1 and theta 2, where I have to copy this. Great. And now, at the end, I have this x cos of theta 2x. So times x times np dot cos of theta 2 times x. And I can return RV. And now this computes the gradient with respect to theta, right? So here we found the partial derivative with respect to theta 1. Here we found the partial derivative with respect to theta 2. But putting those two things together, we get the gradient with respect to theta, because theta is just a vector comprised of theta 1 and theta 2. Great. So now what we want to do is use the gradient of theta that we found in the previous question to implement gradient descent, right? And so just as a refresher, gradient descent is an iterative update algorithm that follows the following form. So our guess for theta at time step t plus 1 is our guess for theta at time step t minus some constant, which you determined in the beginning, times the gradient of our risk function with the theta being at the previous time step. Okay, so as a big picture, what we're doing with gradient descent is trying to find the optimal value of theta that minimizes the risk function. So this is sort of equivalent to what we did in the first question when we took the derivative with respect to theta, set it equal to 0 and solved. But we can use gradient descent in cases where either it's too difficult to analytically solve for the optimal theta, or it's just impossible. Okay, so we're not saying in this case that it's necessarily impossible, but it will make our life much, much easier to use gradient descent. And in the real world, oftentimes you just use gradient descent. Okay, so in the first part, what we want to implement is standard gradient descent. And as it's an iterative algorithm, we probably need to use a for loop, right, to do this however many times we're told. So in this case, we're actually given a parameter, num iter, which tells us how many times to update theta before we say, okay, this is our final guess for. Okay, so what we can probably say is for I in range num iter. And now the first thing we need is the gradient of theta at the previous time step, right? Remember, theta currently is set to theta t, and we're going to calculate theta t plus 1. So the derivative is just the function dt, which I believe is what it was called up here. Yep, x, y, and theta. And now our new theta is going to be equal to the old theta minus alpha, which is one of the parameters that we're given in the problem, times the gradient of the loss at the previous time step, right? This is theta t, this is theta t, and we're setting that equal to theta t plus 1. Okay, so if all we were asked to do is just find the optimal theta, what we have right now would be sufficient. But since we want to plot a few things later in the question, what we want to do is keep track of all of the values of theta. So in this case, if num iter is 20, we want to keep track of the 20 thetas that we find, right? So it allows us to see how quickly we converged. And also we want to calculate the loss at each step to see how much we decrease the loss by at each step. Okay, so what we can say is theta history dot append theta and loss history dot append, and now we're still using L2 loss. So what I can say is average squared loss of y and the sine model of x, theta 0 and theta 1, which is really theta 1 and theta 2. So what we're doing here is at each step with our current version of theta, we're going to calculate the average L2 loss between the true y and the sine model, which is this thing up here, with theta being what it currently is at this stage of gradient descent. Okay, so I believe that's all we have to do for this part. Now, in 3b, we want to use what's known as a decaying learning rate. Okay, so here, the learning rate was just alpha. At each step, we're subtracting by alpha times the gradient at the previous time step. Now, instead, what we're going to do is subtract by alpha times the gradient at the previous time step divided by I plus 1, where I is our iteration number. And we will see some of the benefits of using a decaying learning rate when we look at some of these plots. But for now, let's just implement it, and we'll discuss it a little later. Okay, so really the only difference is we have to change this alpha to be alpha over I plus 1. And so we can copy the rest of our code over. And instead of multiplying by alpha, we multiply it by alpha over I plus 1. We're also asked, why do we need to add plus 1 in the denominator? Because otherwise on iteration 0, we would be dividing by 0. So we can't do that, right? Because I will start off being 0. Okay, so now what we're going to do, we're going to fit, or we're going to use both standard gradient descent and gradient descent with a decaying learning rate to find the thetas that they find in each case. And since we have the theta history and the loss history, what we can do is see how quickly the loss over time dropped with both forms of gradient descent. So we can look at which one converged the fastest. Okay, so first we'll fit, and then also we'll just take a look at the fitted model using standard gradient descent. And we can see it does a pretty good job of capturing the relationship in the data. Okay, so this was using standard gradient descent, but we could also just use the decaying one, and it wouldn't change very much because they eventually converge on similar values. Okay, now what we can do is take a look at right here, the average loss over the iteration numbers, so we can look at which one converges quicker, and you can see that they both converge to having very little loss, and they converge to approximately the same value of theta, but we can see that with using the decaying alpha, it converges much quicker. And the reason that that happens is because if you look at what gradient descent, what the relationship looks like, with standard gradient descent, at each step, we're multiplying the gradient from the previous step by alpha. So it might force us to overcorrect, suppose at our current stage we're larger than the optimal theta. Since we have to subtract by alpha times the gradient, we might overcorrect and become way less than the optimal theta, and then overcorrect again, and then overcorrect again, and eventually it'll converge. But if we use a decaying learning rate, the amount by which we change from our previous guess decreases at each step, so it'll make it easier to converge quicker. Okay, and I realize that was not the greatest explanation, but what we can do is visualize this loss using a few different types of plots, and hopefully it'll make what I just said a little more clear. Okay, so what we can do is take a look at this 3D plot using standard gradient descent, and this is what I really meant by overcorrecting, right? Here, our value might be too big, but then it becomes too small, and then too big, and then too small, and so on and so forth. And then eventually it converges, but it sort of oscillates between being larger than the true value and smaller than the true value. Okay. Whereas if we use gradient descent with a decaying learning rate, you can see that it converges significantly quicker, and it doesn't do this oscillating thing from going on opposite sides of our theta. So hopefully that makes things a little more clear. And that's because the amount by which we change from our previous prediction drops on successive steps, right? Because when you have alpha over I plus 1, when I increases, alpha over I plus 1 decreases, right? And what we can also do is take a look at this, essentially the same relationship with a contour plot. So we will show that first with standard gradient descent, right? And you can see, again, we oscillate back and forth until we eventually converge on the optimal theta, whereas with a decaying learning rate, it will converge significantly quicker and it won't oscillate back and forth. Okay, so hopefully these plots make the difference between standard gradient descent and gradient descent with a decaying learning rate a little more clear. Okay, but if you have any questions, feel free to post about this on Piazza. Okay, so now in number 4, we'll be talking about ridge regression and regularization and the implications that ridge regression has on bias variance. Okay, so now what we're doing is we're taking a look at our loss function. Instead of just being the difference with x, w, and y, we're adding this term lambda times the norm of w, where w is our weights vector. Sometimes we refer to it as theta squared. And what lambda is it represents a penalty on the norm of our weights vector. Okay, so and the reason we do this is it ensures that the entries in our W vector don't become too large, because that represents increased model complexity. So what a larger lambda does, it decreases model complexity. And as we'll talk about after we determine the optimal value, lower model complexity, while it means higher bias, it means lower variance. Okay, and essentially, if our model is less complex, there's a lower chance of it overfitting to our training data, and then therefore not generalizing well to unseen testing data. Okay, so we want to decrease model complexity to make our model more general. Okay, we'll talk about that after we figure out what the analytical solution for W with ridge regression is. So we'll start with that. And really what we're taking a look at is this over here. And this will assume that you've already seen how to derive the solution for standard non-regularized ordinary least squares. Okay, because we'll be using some matrix and vector gradient tricks, and I'll go pretty quickly over that. So make sure you review these sort of steps if you haven't seen them before, and I'll link down below the discussion 7 walkthrough video and the time step you should go to there if you want to see me doing the exact same thing, but just without the plus lambda times W squared. Okay, and so essentially what we're going to do is rewrite the norm of A squared as A transpose A. So we'll get this as XW minus Y transpose XW minus Y plus lambda W transpose W. And then we'll do some simplifying steps. We can write this as W transpose X transpose XW minus W transpose X transpose Y minus Y transpose XW plus Y transpose Y plus W transpose W times lambda. Okay, and we notice these two terms, as we did in the previous video, again, I highly recommend you watch that if you haven't seen it, are really the same thing because they both represent the inner product of XW and Y, i.e. the dot product of XW and Y, right? Because the dot product of A and B is really just A transpose B. And what we want to do is write both of them in this form, because this form is really nice because it allows us to quickly take the gradient with respect to W, which is what we're about to do. Okay, so I'll say that this entire thing is W transpose XW minus 2 W transpose X transpose Y plus Y transpose Y plus lambda W transpose W. And so that's still our loss. Now what we're going to do is take the gradient, or I didn't mean to write that, I meant to write the gradient of our loss. And now we use some of those gradient rules that we saw in the previous video. So the gradient of W transpose XW with respect to W is 2X transpose XW, right? And that uses the fact that the gradient of X transpose AX with respect to X is A plus A transpose X. But if A is symmetric, and in this case A is just X transpose X, which of course is symmetric, we can write this as 2AX if asymmetric. So there's that. Then minus here, that we use the fact that the gradient with respect to X of X transpose A is just A. So we have 2X transpose Y. The gradient of Y transpose Y with respect to W falls out because it's independent of W. And then the gradient of lambda times W transpose W with respect to W is just 2W. So you have 2 lambda W. Okay, that was a lot to take in, but most of it is identical to what we did with standard OLS. Okay, and of course, to optimize, take the gradient, set it equal to 0. Now we solve. Well, first we note that we probably want to collect all of the W's on one side of the expression, and of course we can divide both sides by 2 as well. So we can have X transpose XW plus lambda W is equal to X transpose Y. Okay, and now I can common factor on the left-hand side the W out, and I'll have X transpose X plus lambda. But that doesn't work because lambda is just a scalar, whereas X transpose X is a matrix, right? And so what I can actually do is multiply this by the identity matrix, right? Because lambda W is really the same thing as lambda identity times W. Because multiplying any matrix or vector by the identity matrix does not change it at all. So I can really write this as x transpose x plus lambda I times W is equal to x transpose y. And now I multiply both sides by the inverse of this expression, which is exactly what we did in standard OLS, and we get that W hat for Ridge is equal to x transpose x plus lambda I inverse x transpose y. So notice this is very similar to the solution for standard OLS, but in addition we have this plus lambda I term added. Okay, so I think for the discussion that wraps up 4A. So now we'll take a look at 4B. Okay, so why does this guarantee that we can find a unique solution? Well, it's because x transpose x plus lambda I is always invertible. Okay, and what's the reason for that? Well, so we won't go over the proof right now, but really what you can do is prove that x transpose x plus lambda I is what is known as positive definite, okay, which is a property of matrices, and all matrices that are positive definite are invertible, okay, whereas x transpose x on its own is not necessarily invertible, and there are cases where, if you have fewer observations than features, or if some of your features are linear combinations of one another, x transpose x won't be invertible, okay, so you couldn't use standard OLS. So one of the biggest benefits is that using ridge regression and adding this plus lambda I term, your matrix will always be invertible. So there's never an issue. And if it's invertible, and since inverses are unique, there will always be exactly one unique solution, right? Inverses are unique, therefore unique solution. To answer the question a little more directly. And now, so what are some pros and cons? So again, the pro, as I mentioned before, is that in adding this plus lambda I term decreases model complexity, which makes our model more general, and it will generalize better to unseen data, right? But one of the cons of that is that it will it'll increase our training error, right? Because we're making our model more general. But in the case of our training data, so the data that we're using to create the model, it will actually increase bias, so it'll increase our training error. But in the long run, it'll be more general, so to unseen data, which is what we really care about, the data that we actually want to use for prediction, our model will have lesser variance, which is good. Okay, so those are some of the pros and cons of using ridge regression, and again, this is not a substitute for lecture, so I highly recommend you watch lecture if you still have any gaps in your knowledge with regards to regularization. So C, in ridge regression, what happens if we set lambda equal to 0? So again, just to make it a little more clear, y minus xw squared plus lambda w squared. If we set lambda equal to 0, well then this second term just falls out, and w is just equal to the w we found in OLS, right? Because if lambda is equal to 0, that's just what we had before. Now 2, if we have lambda approach infinity, right, what will happen is the penalty on the norm of w will become larger and larger and larger. Okay, so remember, lambda is the penalty that we have on w. So the greater lambda is, the less complex our model will be. Well, if lambda becomes bigger and bigger and bigger, our model will become less and less and less complex. And so as lambda approaches infinity, our model will approach the least complicated model, which is just 0. Okay, and so another way I like to visualize that is, well, not visualize, but think about it, is in a very hand-wavy sense, pretend that lambda times w is equal to some constant. Okay, now here we're just pretending they're all scalars, but in reality, lambda is a scalar, and of course w is a vector. And if we increase lambda, right, in order to keep the product of lambda and W constant, we'd have to decrease W, right? And vice versa. If we decrease lambda, in order to keep this product constant, we have to increase W. And so you can think of W as being model complexity. So the more we increase lambda, the more we decrease W. Okay, so either way, W will approach the 0 vector. Cool. And lastly, for D, how does model complexity compare between ridge regression and standard OLS? I think we've talked about that enough. As we increase lambda, we decrease model complexity. And to be a little more explicit, as we increase lambda, it increases our bias, but it decreases our variance. Okay, because with more general models, which are the models we have with lower complexity, we're preventing overfitting, but the bias on average may be greater, which is just a consequence of our model being more general. Okay, and again, the smaller theta is, the smaller our penalty on the norm of W is, right? So the smaller theta is, the closer it is to being just standard OLS. So the closer it is to having more variance and less bias. And I think that wraps up number 4, meaning this wraps up the entire discussion. Okay, so feel free to comment on Piazza and the thread where this is posted if you have any questions, or you can even email me. But yeah, I think that's it for today.